Hello students, welcome to EPG Pathshala. I am Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University. Today students, we are going to discuss about the module superconductivity, and particularly in superconductivity the Bardeen-Cooper-Schrieffer theory 1 from the paper Solid State Physics. So students, let us see what we are going to learn in this module. We will learn about the electron-phonon interaction and quasi-particle concept, learn about the Hamiltonian for effective electron-electron interaction, learn about the concept of Cooper pairs, learn to write and understand the Bcs wavefunction and the Bcs theory. So Bardeen-Cooper-Schrieffer were the first to give the microscopic theory of superconductivity in 1957. Their theory correctly explained the isotope effect, that the critical temperature Tc is proportional to m raised to power minus alpha. They correctly predicted the existence of an energy gap 2 delta at the Fermi level. Our main focus in coming slides would be on the first, electron-phonon interaction, 2, Cooper pair formation, 3, Bcs theory and Bcs wave function. So students, now let us start our discussion with this simple electron-phonon interaction concept. So remember that in describing the superconducting state, the Bcs theory plays a very important role, which it was the first theory, and this theory's basis is electron-phonon interaction. So let us try to understand what exactly this concept is. So strong electrostatic repulsion between two bare electrons is basically the Coulomb potential we all are familiar with. That is V, function of r minus r prime. That is, the two bare electrons are placed at coordinates r and r prime is equal to E square divided by 4 pi epsilon naught mod of r minus r prime. Now in the case of metals, quasi-particles exists and effective interaction is reduced. That is, what is the effective interaction? That is above what we have mentioned, is reduced by screening in metals. Using Thomas Fermi model, the reduced potential is V of r minus r prime. In the subscript we have written Tf, which is simply indicating it's a Thomas Fermi approximation, is equal to same Coulomb potential which we have written down above, that is E square divided by 4 pi epsilon naught into mod of r minus r prime, but multiplied by exponential minus mod of r minus r prime divided by the r Thomas Fermi. So this r Tf is basically the Thomas Fermi length. And what is the quasi-particles which we are talking about here? So these are the excitation of a solid consisting of a moving electron together with a surrounding exchange correlation hole. Okay, so this is the quasi-particle we are talking about. So continuing with the concept of electron-phonon interaction. Now the electrons also interact with each other through the phonons in crystal lattice. Okay, so earlier what we have seen is that the direct electron-electron interaction through the Coulomb potential, but the electron can interact with another electron through the crystal lattice. So this is, so we know that the the vibrations of the crystal lattice are called the phonons. Now we consider a phonon with a wave vector q and write the Hamiltonian as h is equal to summation over q and lambda h cross omega q lambda multiplied by a dagger q lambda into a q lambda plus half. So this summation is over each wave vector k and the phonon mode lambda. Okay, so this is lambda is basically the mode, and the a dagger q lambda is a phonon creation operator. That is the creation operator for a phonon with wave vector q and a mode lambda. And in a similar manner, a q lambda is the phonon annihilation operator. And this above equation that you see, that we have just mentioned, is basically, is the second quantized form of a harmonic oscillator. So these phonons are basically the bosons, and they are being treated as harmonic oscillators. So the displacement vector of an atom positioned at with the help of ladder operator is that delta Ri is equal to summation over q lambda epsilon q lambda into h cross divided the under root of h cross divided by 2m omega q lambda multiplied by a dagger q lambda plus a minus q lambda in bracket closed into e raised to power minus q dot Ri. So this atom is now basically placed at the ith position, and this delta Ri is the displacement of that atom, and we are representing the displacement of this atom in terms of this phonon creation and annihilation operator. Electron phonon interaction. Epsilon q lambda refers to a unit vector in the direction of atomic displacements for q lambda mode. Okay, so q is the mode, q is the wave vector and lambda is the mode. Due to the above displacement in the crystal, a deformation potential, that is the effective potential for electrons, arises in the solid. That is delta V1 R is equal to summation partial derivative of V1 R divided by the partial derivative with respect to capital Ri into delta Ri. So this electron diffracts from a block state xi n q, which is basically spatial dependence R, to another block state xi n prime k q as a function of R due to the above potential. Now, in this electron phonon interaction, in this process, overall momentum of the crystal is conserved, and the electron is being scattered from crystal momentum k to the k minus q. That is, either a phonon is created or annihilated. Hence, it is obvious that the electrons at the Fermi surface are interacting. Due to the exchange of phonons, one electron emits a phonon while the other annihilates it, which is just the transfer of momentum from an electron to the another, which is now the basis of the BCS theory. The effective interaction between the electrons turns out to be V effective as a function of q and omega is equal to mod of gq lambda mod square into 1 by omega square minus omega q lambda square. So this q here is the wave vector of the virtual phonon, omega q lambda is the frequency of the virtual phonon, and gq lambda a matrix element for scattering of electrons from k to k plus q state. Gq lambda is actually is very small, as order of 10 raised to power minus 4, and is goes as I mean approximately under root of m small m divided by capital M. So the BCS theory actually tried to simplify the potential by replacing omega q lambda by the d by frequency omega d and gq lambda by some constant, that is g effective. Okay, this is basically just a simplification, and this interaction that you're saying, this matrix element could be, like this potential, it is defined, like in this way, that repulsive potential exists for omega greater than the d by frequency omega d, and it is attractive for omega less than omega d. So that is basically this V effective simply changes sign in these two limits, repulsive and attractive. Now, BCS, the theory, propose that our main concern is with the electrons having energy such that and lie within the Fermi energy. Hence, BCS theory tells us that mod of omega should be less than the d by frequency omega d. That implies that this V effective potential that we mentioned is negative of the mod of G effective whole square. So the effective Hamiltonian for effective electron-electron interaction simplifies to be following in the condition that this electron-electron interaction is basically H1 is equal to minus mod of G effective square summation over this product of 4 operators, that is 2 creation operators C dagger K1 plus Q sigma 1 and C dagger K2 minus Q sigma 1 into C K1 sigma 1 C K2 sigma 2. And remember that the condition being that under which it is effective is that mod of epsilon Ki minus mod of epsilon F, that is, remember epsilon F is the Fermi energy, is less than H cross omega d. So here you see that we show here a figure depicting the electron phonon interaction. This is the what is called as the Feynman diagram. This is effective electron interaction near the Fermi surface. You can clearly see here, like the electron with wave vector k1 spin sigma 1 becomes k1 plus q, sigma 1 remains sigma 1, and the other electron k2 sigma 2 becomes k2 sorry minus q and the spin with sigma 2 interactions. You see, this is what we have mentioned, that the 2 electrons are indirectly interacting via the phonon. The 2 particle wave function of these extra electrons with center of mass R subscript Cm is equal to, that is the psi is equal to, which is basically function of R1 R2 sigma 1 sigma 2, is equal to e raised to power iota k Cm dot RCm multiplied by a function which is depends upon the spacing between the 2 electrons, that is R1 minus R2, is basically spatial dependent function multiplied by a spin dependent function, that is phi spin, which depends upon sigma 1 and sigma 2, where this R center of mass is equal to R1 plus R2 divided by 2. The total momentum of the electron pair is given by H cross multiplied by kcm. Now this kcm is equal to 0. So this implies that the ground state with minimum energy, and the spin wave function can be written as singlet and triplet. So in this case the spin singlet is written as 1 divided by under root of 2 with multiplied by a state where that's the first electron is up spin, the second is down, minus the state where the first electron is down, the second electron is up. And in the case of spin triplet state, we have got 3 possibilities. That is, either we can have that both the electrons are up state or both the electrons are down state, or is equal to 1 by root 2 whole multiplied by a state with first up, the second down, plus the first down or the second up. So there is here, remember, again repeating that this sigma 1 sigma 2, remember these are the spins of the 2 electrons, and R1 R2 are the coordinates. So basically, quite typically that what one does is that the total wave function is written as a product of the spatial part and the spin part, is exactly what we have done here. And the exponential term e raised to power iota k center of mass dot R center of mass is basically kind of a plane wave representation. Now proceeding ahead, we expand in terms of the block wave as follows. The spatial part of the wave function is written as summation over k multiplied by phi k into e raised to power iota k R1 minus R2. So this phi k is an even function. The full pair wave function, that is electron pair wave function using Slater determinants with the restriction that k is more than kf, can be written like this: that's summation over k multiplied by phi k multiplied by a matrix with the the diagonal elements, 2 by 2 matrix with the diagonal element as wave function with the vector k in coordinate space r1, that is this electron, with upspin, and the other diagonal element is with the electron in the r2 coordinate, downspin with momentum minus k. And the off diagonal elements are like this, as shown, that in the top one, where you have see that the in the second column, the first entry in the second column is the coordinate as a function of r2, downspin, and then with the momentum k, the wave vector k. And the other one, like exactly opposite, that the it is placed in r1 coordinate with upspin minus k wave vector. So our equation now pairs up all the electrons at k with those of opposite spin minus k. So you see the summation here is over k. So all of the electrons are paired. On substituting above in the Schrodinger equation, we get the following solution. That is, E of phi k is equal to twice of epsilon k phi k minus mod of G effective square into summation over k prime phi k prime. E is the total energy for two particle system and is relative to the Fermi energy level. This figure shows the Fermi surface where Cooper pair formation. So as you can see, we had discussed, like the Cooper pair formation is between two electrons with opposite momentum, that is k and minus k, and clearly this blue dots are the two electrons and they are completely on the opposite side, one plus q and the other is minus q, okay, or plus k minus k. So in order to get the last equation that we had shown in the previous, that is substituting the wave function into the Schrodinger equation, what we do is that, like this wave function, this xi ket vector is equal to summation over k phi k multiplied by the xi and the ket vector xi as a function of k, that is that kth wave function. We put it into the Schrodinger equation, h xi is equal to e xi, and then taking the product with the, like you're multiplying from the left this bra vector, that is how you basically find out the eigenvalues. So the effective interaction takes k prime minus k momentum from this electron and it transfers to the other electron, which means that a pair of electrons k and minus k converts to k prime and minus k prime, having a matrix element minus mod of G effective square. Also, the limit that epsilon as a function of k less than h cross omega d limits the k into a thin shell. It limits a k into a very thin shell. This is not the entire sea of Fermi electrons is involved now. Here implies that the group velocity of the block function at the Fermi surface. Using the self-consistency equation, that is C is equal to summation over k phi k, we get 1 is equal to minus mod of G effective square summation over k 1 divided by E minus 2 epsilon k. Integrating the above equation within the proper limits, what we can get is that this lambda which we were talking about, this lambda is equal to mod of G effective square into G as a function of epsilon f, and minus E is equal to twice of h cross omega d into e raised to power minus 1 by lambda. Conclusions. Now we can say that a bound state exists near the Fermi surface whose energy is small when lambda is very small, but we should always keep one thing in mind, that an attractive interaction in 3D is not the only cause for the bound state. The field Fermi C also plays a key role in the BCS theory. Also, the wave function phi is that we can be independent or dependent upon the direction r1 minus r2 of creating S wave or D or P wave pairing of electrons. But mostly the superconductors choose a S wave singlet pairing state. Also in BCS theory, S wave state is used as here electron-electron interaction is independent of the Phonon wave vector q. But other types of interactions can allow other pair types to exist. For example, in superfluid helium-3, Cooper pairing is p wave and spin triplet. So, using Fourier transformation, we get the point contact interaction as V effective R1 minus R2 is equal to mod of minus mod of G effective square delta function of R1 minus R2. The BCS wave function. During Cooper problem, BCS realized some difficulties. First was that the whole Fermi surface is not stable for the creation of Cooper pairs, as every electron becomes bound due to attractive interaction near the Fermi surface. Secondly, it was difficult to express many particle wave functions where every electron is in bound state. So, the many body wave function is written like this, which is basically a summation over all these wave functions. Simply writing as above is not satisfactory because the macroscopic quantum coherence phenomenon, which is essential for condensates and superconductivity, remains unclear with this kind of wave function. So, Schrieffer took the initiative to write down a coherent state of Cooper pairs. He used the electron pair annihilation and creation operators which do not follow normal Bose commutation laws. Now, the BCS wave function that we want to talk about, the pair creation operator and a coherent state many body wave function can be written like the way it is done here. So, we introduce this operator pk dagger is equal to ck upspin dagger c minus k downspin dagger. In a similar manner that when we multiply, that is pk dagger into pk dagger, it becomes 0. So, you can try out actually doing this, that why it is 0. You can sort of use the basic commutator and anti-commutator relations here, and remember that pk dagger and the commutator of pk dagger and pk prime dagger is always equal to 0. Commutator of pk dagger is not equal to 1. ck up spin dagger into ck up spin dagger is equal to 0, and pk dagger whole square is also equal to 0. So, the BCS wave function is motivated from the coherent states in quantum optics. So, this BCS wave function is written as a constant multiplied by exponential summation over k alpha k pk dagger multiplied by the vacuum state. Here the vacuum state implies 0 electrons at the Fermi surface, and alpha k is just a parameter to minimize the energy. Now, we can write one coherent state for each k as the following, that this BCS wave function is equal to constant product of the k exponential alpha k pk dagger multiplied by the vacuum state. Expanding the exponential term in above equation and neglecting the terms quadratic or higher power in pk dagger, we get the following result, that the BCS wave function is equal to constant multiplied by the product of the over the k 1 plus alpha k pk dagger whole multiplied by the vacuum state. To find the normalization constant, one can use the following expression, that 1 is equal to 1 plus mod of alpha k square. So, the final normalized BCS state then is equal to the BCS wave function is equal to the product state, this product is over k uk star plus vk star into pk dagger whole multiplied by the vacuum state. So, where this uk star is equal to 1 divided by 1 plus mod of alpha mod of square, vk star is equal to alpha k divided by 1 plus mod of alpha k square, where this mod of uk square plus mod of vk square is always equal to 1. So alpha being a complex number, a phase angle theta can also be associated with the above BCS state. The capital N, which is the number of particles, is not fixed, which according to BCS was having an uncertainty of the order of square root of n. Finally, the BCS state can be written, which includes both electrons and concept of hole. BCS state can be viewed as condensate of electron pairs above filled electron Fermi C and a condensate of hole pairs below an empty hole C. So the final BCS state is something like this that you see here. In this module, we have studied about the basic concept of electron-phonon interaction and how two electrons behave differently when bare and when in metals. The formation of Cooper pair and how momentum gets transferred from one block state to another. The many-body wave function, pair creation operator, and also the whole concept in BCS theory. Thank you for visiting ePathshala.